totally reasonable. So there we go. So reactions of alkenes. So just to recap what we went over last class, you can still see all my scribbles on here. So we said addition reactions is what we're going to focus on this chapter. And it's the opposite of elimination. So elimination reactions, E1, E2 reactions, those were covered in chapter 7. And so now we're going to take the two carbons of a double bond and we're going to be adding two different moieties or pieces to the two carbons of a double bond. And we said, well, a pi bond is weaker than a sigma bond, and that's why alkenes are reactive. Okay, so we went over that. Then we said we're going to take a look at all of these different types of additions. But again, one of the things I want to focus on with you today is going to be the Markovnikov rule. Okay, so Markovnikov addition and then anti-Markovnikov addition. And provided we have time, we'll get into some hydrogenation and halogenation reactions as well. But if we go back here, you can see what all of these have in common. You're taking a pi bond, right? You're taking the double bond in your starting material and you're adding something to each one of those carbons that was formerly in the double bond. Give me a thumbs up if you're with me on that. Everybody with me so far? Okay, cool. So we got a bunch of different reactions to cover. And something that we want to keep in mind as we move forward is that a pi bond can act as a base or a nucleophile, depending on the situation, right? If we treat it with an acid, it's going to act as a base. And you see we end up with a carbocation there. But it can also act as a nucleophile if we put it in the presence of a strong enough electrophile, right? If an electrophile has a positive charge right on it, that's a very strong electrophile. And so we get another carbocation there. Do you guys remember carbocation stability? When it came to primary, secondary, and tertiary, which one was the most stable of all of them? The tertiary, right? So we have tertiary carbocations are more stable than secondary, which are more stable than primary, and then we have the methyl carbocation, which would be the least stable of them all. Now, alkenes in nature and industry, if you want to read this section, it talks about terpenes a little bit, and terpenes are natural products, so naturally occurring molecules that have a number of carbons that is some kind of multiple of 5, so 5, 10, 15, 20, et cetera, et cetera. And if you look at the compounds on here, these are terpenes. So I talked a little bit about limonene, and you can see how that's a chiral compound, and then we have this other compound here, which is found in black pepper. All right, and then we said carbon-carbon double bonds are also found in many pheromones. And if you remember what a pheromone is from your biology class, it's some kind of compound that's going to elicit some kind of response in a member of the same species. So you see some different pheromones here. Anyhow, then I talked a little bit about petroleum, right? Petroleum is always in the news, but I'd say it's in the news a little bit more than usual lately. And what are two of the main components that we get out of petroleum? Well, you see here that these two alkenes are two of the major components, so ethylene and propylene. Now, these are common names. Ethylene is a common name. Propylene is a common name. You could give them a systematic name, which is also accepted by UPAC. So you could also call this molecule ethene, and you could call this molecule propene, okay? Now, sometimes students will want to call it 1-propene, but that would be redundant because there's only 3 carbons in there, ergo it has to be between the first and second carbons. The only time when we start, I should say, using a locant for the double bond is when you have 4 carbons, right? We could have 1 butene and 2 butene. Okay. All right, so alkenes, ethylene and propylene are used to make many different compounds here. And I would just invite you to take some time to take a look at these compounds. You should have an idea where organic molecules come from after studying organic chemistry. And so you can see here, I highlighted these 2 compounds, the 2 glycols, which are major components of automobile antifreeze. Then we have acetic acid, which we talk about all the time in this class. We talk about it a lot in general chemistry. Polyvinyl chloride, ethanol, different compounds that you know. Also, isopropyl alcohol. Does anybody know where we would find isopropyl alcohol in our everyday lives? It's rubbing alcohol, right? That's rubbing alcohol. If you buy rubbing alcohol at the drugstore, then we have acetone, which, as you told me last class, is nail polish remover. Anyhow, now when it comes to the nomenclature of alkenes, if you weren't here last class, I can cover the rules for naming an alkene very quickly. If all the same rules that we used in chapter 4 for naming alkanes and cycloalkanes, they still apply. The only thing is that now our longest chain has to contain the carbon-carbon double bond, okay? So we're going to identify a parent, again, parent is the longest chain, but this time it's got to include the double bond. Thus, it might not necessarily be the longest chain of carbons, but again, it has to be the longest chain that contains the double bonds. Furthermore, if you have two double bonds, both of those double bonds would have to be in the longest chain. Okay, so we always want to make sure those double bonds are part of our parent. Then we just identify and name the substituents, assign a number and a prefix, give the carbon-carbon double bond the lowest number possible, and we're going to talk about that. Put the substituents in alphabetical order like we always do. We ignore prefixes except iso, cyclo, and neo. We don't really see neo in this class, but we do see cyclo from time to time, so keep in mind that for iso, you alphabetize according to the letter I, and for cyclo, you would alphabetize according to the letter C. And then for the locant, or the number for our carbon-carbon double bond, it can either be placed before the parent or before the -ine suffix, and I'll show you examples of that. So, again, if we have pentane and we put a double bond in it, we change the suffix from -ane to -ine. And you see here we have 1 pentene. Again, we will seek to give that double bond the lowest possible number, but you see here we have 2 pentene as well that I put up above it, right? We want to give, again, the carbon-carbon double bond the lowest possible number. Now, again, you can put the locant, the number, either before the parent or you can put it before the suffix. Either one is acceptable. And again, when that comes into its own is when you have multiple functional groups. You'll see the utility of that as we move forward. However, if I give you a relatively straightforward kind of nomenclature example, either one is totally fine. And yeah, so there we go. So longest chain contains the carbon-carbon double bond. Again, we number from the side that gives the double bond the lowest possible number. And one more thing that I told you is that if you have a ring, and I went over this a little bit last class, if you have a ring, let's say like this, and then you've got a substituent over there, remember, your first 2 numbers have to go through the double bond. So it would either have to be 1, 2, which would be wrong, or 1, 2, which would be correct, right? Because then we would give the methyl group the lowest possible number, right? If we went around the other way, it would be 1, 2, 3, 4, 5. Okay, so 4 is lower than 5. So again, the first 2 steps in a ring that contains a double bond always has to be through the double bond. All right, you with me on that? Okay, cool. And then as far as double bonds go, we can still use the identifiers cis, trans, E, and Z. We like to use E and Z, it seems, a lot in this chapter. And so if you have one double bond in your chain and it's E or Z, you do not have to put a locant in front of it, right? You see there's no number there. It doesn't say 2E 5,5,6 trimethyl hept 2-ene or 2-heptene, right? They leave that out. When you have more than one double bond in your molecule, then you have to use a locant. Are you with me on that? Okay? Because if you only have one double bond, it would be redundant to put a 2 in there, right? Because you see that it's this carbon here. All right? So with all that in mind, let's see if we can tackle some of these. Look, I used the same example twice, so maybe I'll just erase this out of here for now. So let's take a look at this first one. And you notice something about the double bond and the longest chain. You notice there's some symmetry in the longest chain, right? We could start here 1, 2, 3, or we could start over here 1, 2, 3. Either way, this is some kind of 3-hexene. But which numbering system is correct? Only one of them can be correct in this case. Anybody? It's the blue one, right? Because then it gives the methyl the lowest possible number. So we'll get rid of those, and we'll say 1, 2, 3, 4, 5, 6. So we've got a 3-methyl, and then we've got a 3-hexene. So we'll put that down here. So we'll put 3-methyl, 3-hexene. Okay. And if you want to put 3-methyl hex 3-ene, that's perfectly fine. However, we do have to designate this compound as being an E or a Z compound. Could anybody tell me by inspection, is this an E compound or a Z compound? It would be a E compound, exactly. This is an E compound. So we'll just scribble this down here. We put the E in parentheses, and so there you go. We went ahead and named this one. I would also say you could call this compound a trans compound too, because you've got the 2 ethyl groups that are trans to each other. So I would accept either one, okay? All right, so we got that guy. Now with the next one, We want to seek to find the longest chain that contains the double bond. It has a total of 1, 2, 3, 4, 5 carbons if we go like this. It doesn't matter which side of that kind of isopropyl-ish branch you go, you end up with the same thing either way. And we want to start numbering here to give the double bond the lowest possible number. So this is some kind of 1-pentene. Are you with me on that? Okay, so we could just start with that and we could say this is some kind of 1-pentene. Okay. However, we've got some substituents here. You notice we have methyl groups at carbons 2 and 4. So we have a 2,4-dimethyl. And then could anybody tell me what substituent is this guy here at carbon number 3? That's an isopropyl, isn't it? Right? And I comes before M. And so the isopropyl is going to come first. So we've got a 3-isopropyl. So let's see if I can put this all together. So 3-isopropyl. Then we've got a 2,4-dimethyl 1-pentene. 2,4-dimethyl, look at that, pretty good. All right, dimethyl 1-pentene, or you could call it 3-isopropyl 2,4-dimethyl pent 1-ene. Either one is perfectly acceptable. All right, got that one. Now, why didn't I put E or Z for this one, or cis or trans? Because you guys remember that if we have two groups that are identical on one of the carbons of the double bond, it can't be cis, it can't be trans, it can't be E, or it can't be Z, right? It doesn't have any effect on this, or it wouldn't be correct, okay? Anyhow, with the last one, the next one, we have a diene, so we have 2 double bonds in there, and I think you could probably all identify 1, 2, 3, 4, 5, 6, 7. Okay, so this would be not a heptene, but a heptadiene is what we would call this, okay? And you can see the double bonds are at carbons, so if we number 1, 2, 3, 4, 5, 6, 7. So we would call this a 1,5-heptadiene is the way we'd name this. So I'll scribble that down here, 1,5-heptadiene, all right? Then we have 2 substituents. We have a chlorine at carbon 5, and we have a tert-butyl at carbon number 4, all right? And what should come first, tert-butyl or chlorine? Tert-butyl should come first, shouldn't it? All right, so I'm just going to move this out of the way, make sure I have room. So I'll put the 4-tert-butyl, so 4-tert-butyl, 5-chloro, so 5-chloro, 1,5-heptadiene, so let me move this over like that. Now for the first double bond between carbons 1 and 2, is E or Z relevant for that carbon? The answer is no. But E or Z is relevant for this this double bond right here. So would this be an E double bond or a Z double bond? It would be Z, right? Because the chlorine takes priority and the methyl group takes priority. Yes, so this is a Z double bond. And so, since we only have to provide a stereochemical designation, E or Z, to one of the double bonds, the other one would be redundant, okay, or we couldn't assign one. So the reader of the name knows that the stereochemistry lies in the double bond at carbon number 5, right? Because there can't be anything at carbon number 1. And so we don't have to put a locant here. We're just going to put Z, okay? Are you with me on that one? All right, and the last one, did anybody name this one while I was yammering on here? We've got a cyclopentene. So we go from cyclopentane to cyclopentene. I'll just ask you guys, should I start numbering on this carbon I have highlighted in green or on this carbon I have highlighted in blue? Which one? The blue one, right? So we're going to have 1, 2, 3, 3. So we're going to have a 3,3-diethyl cyclopentene. Great. Good. 3,3-diethyl cyclopentene. Cyclopentene. Great. Wunderbar. Perfect. All right. So the next section, 8.4, I don't know really what I'm going to test you on about this. Okay, it's I wouldn't say it's an FYI section, but you think about anything that you've done well on in a class, it's usually something that you understood, right? It's usually something where you're like, yeah, I get that. That makes sense to me, okay? And so this section, 8.4, just deals with a little bit of the thermodynamics of addition, which is what we're going to focus on in this chapter, versus elimination, which is what we focused on in chapter 7, right? It was half of chapter 7 was E1 and E2. So if you're wondering, okay, you taught me how to do elimination reactions, right, with all these strong bases, sodium methoxide, tert-butoxide, DBU, DBN, all that good stuff, okay? Well, why is it that sometimes I'm going to get addition and then other times I'm going to get elimination? Well, it has to do with both enthalpy and entropy, okay? And so what we're going to do is we're going to take a look at these two terms very quickly, okay? We're not really going to spend a lot of time quantifying them, but I'll ask you guys something that you would have learned in chapter 6. Is entropy increasing or decreasing when you do the addition reaction? So as you do addition, is delta S increasing or decreasing? It's not a trick question, it is decreasing, right? Because you're going from 2 molecules to 1 molecule, right? So you're going from 2 species to 1, so it's becoming more organized. So our delta S is actually decreasing there. Now, I think you guys could probably figure this all out without any help from me as well. Let's just revisit. What is stronger? So I asked before, what is weaker? What is stronger, a sigma bond or a pi bond? A sigma bond, right? Pi bonds are weaker. And so if we look at the reaction, an addition reaction, we see that we're breaking 2 bonds. We're breaking a pi bond, easy to break, weak, and we're breaking a sigma bond during this addition reaction of HCl across this double bond. But what are we forming? We're forming 2 what kind of bonds? Sigma bonds, right? We're forming 2 sigma bonds. Now, you're like, it's all coming back to me now. Oh yeah, remember that formula you taught me, right? Delta H of a reaction was bond dissociation energies of bonds broken versus bonds formed. Well, think about it. You have bonds broken, less energy, right? Because there's a pi bond in there. There's a sigma, but there's a pi, so that's less energy. Subtract 2 sigma bonds being formed. So you're taking a lower number, subtracting a bigger number, so you get a negative number. So you get an exothermic process, all right? So our delta H is negative, right? But we have to think about the whole delta G is equal to delta H minus T delta S, like this. So already we've solved, and we said our delta H is a negative number. Now you guys told me that the delta S was a negative number. Yes, the entropy was going down, so we've got a positive number for our T, multiplied by negative here. So we have a negative subtract a negative. Well, when is the delta G going to be negative? Well, let's take a look, and I know you guys can do the math, okay? So if we take a look here, well, when it says here at lower temperatures, the enthalpy is going to dominate, right? At a low temperature, okay, your enthalpy is going to dominate, delta H, and addition reactions are going to be favored. However, if your T is too high, then the second term becomes too big, and you end up with a positive number, and elimination reactions are going to be favored. So what's our conclusion? So I'll write delta S over here, is that these reactions are going to be governed by temperature. If we're at a lower temperature, the enthalpy term is going to dominate, and then we end up with our addition reaction occurring. However, if you turn up the temperature too high, then we're going to end up with the elimination reaction. Now, before you run wild with this and just say, okay, low temperature addition, high temperature elimination, the textbook actually gets into this like in a blurb about this long. It's like 1 sentence. And he says, like, hold your horse. It doesn't work exactly like that because a lot of times in organic chemistry, if you heat up the reaction too much, everything just degrades, okay? It just doesn't work. All you need to know is that in order for addition to be favored, what kind of temperature are we going to use? Low temperatures, right? So a lot of the reactions that are done in this chapter are going to be done at low temperature. I'll just be honest with you, it doesn't even mention temperature all that much moving forward in this chapter, but it will be important in a couple of cases. We'll look at a reaction with potassium permanganate later on that occurs at a low temperature. But that's about the crux of it, okay? That is what I want you to know, okay? Low temperature, addition is going to be favored. Higher temperature, elimination is going to be favored if everything doesn't get burned up. All right, so let's move on. And you ready? Okay, now we're going to get into the real serious part of the chapter. We're going to do a journey through all these different reactions. We're going to start with hydrohalogenation, hydration, hydrogenation, halogenation, halohydrogen formation, all these different things. All right, ready? Here we go. If you take an alkene. You're walking down the street, you see an alkene, you're like, I could do a reaction with that, a chapter 8 reaction. I could treat that with some HBr. Notice we're at low temperature because low temperature favors addition. And I end up adding HBr across the double bond is the way we would describe it, right? Because you're adding this hydrogen, which is not drawn in, okay, right? Because this is a proper bond line structure. But we're adding HBr across that double bond. You with me on that? Now, would you agree with me that there is symmetry in this starting material, right? You would agree with me that there's symmetry in this molecule, which is what? Cis-3-hexene. Okay, so we have symmetry in there. And so it doesn't matter where you put the hydrogen and where you put the bromine, you're going to get the same compound either way. Now, I know you guys probably recognize that there's a stereocenter in here, and we'll address that in just a little bit. Okay, so just wait, and we'll take a look at that in a little bit. However, when it becomes more interesting is if you have an alkene that is not symmetrical. Maybe I should use a different color here. So not symmetrical, like this example here. Right? If we zoom in, you guys would agree that that double bond is not symmetrical. On one of them, there's one methyl group, and on the other one, there's two methyl groups. So obviously, there's no symmetry in the molecule. Thus, there's two possibilities. Where does the X go from your halogen? Whether it's chlorine, bromine, or iodine. Remember, that's what X represents. So X represents either chlorine, bromine, or iodine, not HF. Okay, so we don't use fluorine, and we talked about that already. But anyhow, the question that we need to answer is, where does the halogen go? Does it go on this carbon? Does it go here? Okay, or does it go on this carbon over here? And this is what we're going to study for the next few minutes. And halogenation is regioselective for what we call Markovnikov addition. So the rich get richer is sort of the expression that we use. Students seem to like that expression. It's easy to remember, right? The rich get richer. Here's the answer. Whichever carbon of the double bond is richer in hydrogens, which is just another way of saying has more hydrogens on it, that's the carbon that's going to take the hydrogen, the HX molecule, HCl, HBr, or HI. The other carbon that is poorer in hydrogens will take the halogen. Markovnikov addition. Okay, that's what we call Markovnikov's rule. And you see that he learned this a long time ago, 150 years ago. Markovnikov observed that the hydrogen atoms tend to add to the carbon already bearing more hydrogen atoms. So this carbon is the one that has a hydrogen on it. You can see the other carbon has no hydrogens on it. And thus, this is the carbon that takes the hydrogen. The other one has the halogen. Now, if you're sitting there going, why does that happen? Don't worry. I'm going to give you a good explanation in just a few seconds, okay? And this is why I mentioned carbocation stability a few seconds ago. The halogen is generally installed at the more substituted carbon, which just is another way of saying the rich get richer. All right, now why would this be? Well, we're going to uncover that in just a second. However, when Markovnikov initially started working on the idea of hydrohalogenation and where does hydrogen go and where does halogen go, at first he was getting all kinds of strange results. And Markovnikov, is the way I remember hearing about it when I was a student in this class, was kind of an interesting person. He had a law degree, so he was a lawyer. He was also a chemist in his spare time, right? I think, maybe he'd really repair your shoes, while you're waiting or whatever. Anyhow, so the guy had many different hobbies, or interests, I should say. And he was studying the Markovnikov addition, or what we call Markovnikov addition now, and he was noticing that sometimes he got the opposite regioselectivity, that the rich did in fact not get richer. And he was trying to figure out why, why is this happening? And if you look in the book, he briefly mentions that, it's 1869, it's a long time ago. They had all kinds of weird, or strange to us, ideas. And they said, maybe it's got something to do with the phases of the moon. Okay, the phases of the moon are affecting the reactivity here. However, what he discovered was it had to do with the purity of his solvents. That's what it was all about, okay? When the solvent was purified, he ended up getting the Markovnikov addition as we know it, okay? When the solvent was old and wasn't purified, he ended up getting the opposite. He got what we call anti-Markovnikov addition, and the impurity that was in his solvent was a peroxide. Now, I've taught this class long enough that ROOR, my students call it ROR all the time, okay? we should know the proper term. I'll say, what's the reagent? And they'll be like, roar? And I'm like, no, it's a peroxide. Okay, you guys remember H2O2, right? This would be R2O2, but it's not a hydrogen peroxide. It's an organic peroxide. And I'll show you a couple of organic peroxides. So this is a peroxide. And the reaction mechanism is different for the anti-Markovnikov addition with the peroxide than the Markovnikov addition without the peroxide. So that's what we have to remember. If we just take HBr, we get the Markovnikov addition product. If we use HBr and the peroxide mixed in, we end up with the anti-Markovnikov product. And this mechanism, okay, this mechanism will be covered in detail in Chapter 10. It's the last chapter of new material that we look at in this class, okay, because Chapter 11 is just review. But let's move on. Now, the important lesson here for you and me, what's so great about this, is that you can control the regioselectivity depending on which reagents you select. You select HBr, the rich get richer. You select HBr and put a peroxide in there, the opposite happens, okay? The carbon that was richer in hydrogens is the one that accepts the bromine. So we call the normal one, I shouldn't say normal one, we call the first one Markovnikov addition, and we call the second one anti-Markovnikov addition, okay? You're going to hear a lot about this in this chapter and every other chapter that you cover in organic chemistry moving forward. So by the time the class is over, trust me, you're going to know your Markovnikov rule off by heart. But let's just see if we could draw a couple of products here of Markovnikov and anti-Markovnikov addition. If I highlight this carbon in yellow and I highlight this carbon in red, we're doing addition with HBr, no peroxides, and so which mechanism is going to predominate, or which regioselectivity would predominate? Is it Markovnikov or anti-Markovnikov? It is Markovnikov. So I'm just going to write Mark, period, for short. Now, could you guys tell me which one of these two carbons is going to accept the hydrogen? The red one, right? Because it's richer in hydrogens. It has one hydrogen on it. The carbon in yellow has 0 hydrogens on it. Therefore, it will accept the bromine. And so our final product is going to look something like this, where this carbon has accepted the bromine. If you're still need this as a security blanket, if you're like, you know what, I need to draw that hydrogen in, but go ahead when you're practicing. But technically, you guys know we don't normally do that unless we're specifying this proton is involved in a reaction or something. So if you need to do that while you're studying, go ahead. You won't offend me, but we know that this is actually a more correct bond line structure. Now here we have, we'll say this carbon is in red, and we'll say this carbon is in green. Which one of those carbons is going to accept the proton? If we're doing anti-Markovnikov addition, as you can see we are, because we have a peroxide, so anti-Markovnikov. The green one is going to, sorry, what did I say, the proton, or did I say the bromine? Did I say the proton? Sorry, you were right. Okay, I thought I said the bromine. The one that's going to accept the proton is the red one because it's poorer in hydrogen. Sorry, that was a bad time to do it, misspeak, huh? But anyhow, so you're like, now you're shaking my foundations, all right? But anyhow, anti-Markovnikov addition, I'll repeat, the carbon that's richer in hydrogens is the one that will take the bromine. All right, there we go. So we end up with a primary alkyl bromide. I know what you're thinking. Think of all the SN2 reactions I could do with that, right? I could make an ether with that. I could make a thiol with that. I could make an alcohol out of that, right? I could take acetate and make an ester, right? This is the way we start to think as organic chemists, right? We start to get excited when we see different molecules. Okay, I'll try not to misspeak on this one. What about the first one? Okay, is the first reaction, and I'll hide this one here. Is this a Markovnikov addition or an anti-Markovnikov addition? This one here. It would be Markovnikov, right? So for this one, we're just going to write HBr. And I'm going to give you a second to write down the conditions for the second reaction, okay? If it's anti-Markovnikov, we got to remember these conditions well. Anybody can tell me what it is? It's going to be HBr and, not roar, HBr and a peroxide. There we go, HBr. Come on, it's day one. Let's call it a peroxide, okay? Maybe if we're in like chapter 19 and we haven't thought about it for a couple of days, I'll let you get away with the roar, but for now we're going to call it by its proper name, okay? A peroxide. Great, great. If you look at any of the ACS study guides, MCAT study materials, DAPMET study materials, I can promise you, okay, that Markovnikov and anti-Markovnikov addition is tested highly by all of these standardized exams. Now, just like a magician, you want to see why? You want to see the reason? Okay, here's the reason. What did you guys tell me? What's more stable, a tertiary, secondary, or primary carbocation? Which one's the best? Tertiary, right? So check this out. Here's what's going to happen. You have these two carbons in your molecule. Well, the carbon that is richer in hydrogens is going to accept the hydrogen in the first step, right? It's a proton transfer. Why does it do that? It's because you end up with the more stable carbocation. Now, you guys don't have to write this down because I'm going to kind of like half rebuke it. But if I draw a quick mechanism down here at the bottom, and again, don't draw this because it's not what's happening. But if, in theory, we had something like this, okay, where this carbon is accepting the hydrogen, then I end up with this, which is a secondary carbocation. No, bad, right? It's not nearly as stable as a tertiary carbocation. And thus, this is why we see the regioselectivity we do. And if you're sitting there going, it's just about carbocation stability, that's it. That's why the rich get richer, because we end up with the more stable carbocation as our what? Intermediate, right? Remember intermediate in the SN2 process? And so, again, here's our intermediate. Intermediate. And a tertiary carbocation is more stable than a secondary carbocation. Thus, the formation of the secondary carbocation would have a higher what? A higher activation energy, right? It just takes more energy to make it. And so that explains Markovnikov addition of HX, okay? Of HX. And we're going to see it's a similar thing for adding water across a double bond as well. There you go. That's it. Now, this is the mechanism that Mr. Dion drew a couple of slides ago, okay? You don't have to, you're never going to be asked to draw this on a quiz or exam, right? Because it's incorrect. But I do expect you to be able to draw this mechanism, okay? I do expect you to be able to draw the proton transfer, form the more stable carbocation, nucleophilic attack, and well, I didn't even put the nucleophilic attack in here, but there you go. Again, I'm repeating myself like an old person. Markovnikov product is formed why? Because carbocation stability. All right, that's it. Who likes this? He's like, you know, at least it's logical. At least there's some logic to it. Yeah, totally, there's some logic to it. Now, again, this is just looking at the first step of the hydrohalogen or the hydrohalogenation. So you've got your first step and your second step like this. This is just zooming in on this first step and just comparing the formation of a secondary carbocation versus a tertiary, and you can see for the secondary the activation energy is higher. Nothing more than that. Now, I know you guys are very astute, and you know that if you were to react this molecule with HCl, okay, so if I react this with HCl, and one, like, I will use the word trick. One trick I like to use, and I learned this, you know, when I started studying organic chemistry, is sometimes you'll see me drag the curved arrow on purpose through the carbon where the bond is being formed. I do this deliberately, especially because I'm a teacher, okay? So what I'll do sometimes is I'll drag the curved arrow through the carbon that's accepting that hydrogen just to kind of make it more clear for you guys, right? In the textbook, it's probably just that, but I'll do this a lot. I'll drag it through the carbon to show you it's going on to this carbon, okay? That's where the proton is going. And so we end up with this secondary carbocation like this as our intermediate. But let me ask you guys, what's the hybridization of that carbon? It's the carbocation. It is sp2, okay? If it's sp2, what's its molecular geometry? Trigonal, planar, right? See something? This, right? Flat as a pancake, right? It's trigonal planar. So let's write that down. Trigonal planar. And so one thing I noticed in chapter 5 is that you guys are very good at visualizing things in 3 dimensions, right? And so if the electrophile is flat, that means the nucleophile is going to attack either side indiscriminately. Thus, when we form a chiral center, we're going to end up with a racemic mixture. In other words, the two enantiomers are formed in equal amounts, We can call this a racemic mixture. You could put, these, you could put 50-50, whatever you want to write. But we end up with an equal mixture of R and S in this particular case. All right, now let's finish out this mechanism. So I'll just put the chloride in here, which is our nucleophile, and then the nucleophile is going to attack the electrophilic carbon. And so there is your mechanism for your hydrohalogenation. Markovnikov addition. Again, the mechanism for anti-Markovnikov addition will be covered later on. I'll go through it in detail. Does anybody remember, just by perusing the textbook, what chapter 10 was about? Does anybody remember what the topic of chapter 10? You're like, okay, the topic of chapter 10 is radicals. You guys remember what a radical is? Right? Unpaired electrons. Do a whole chapter on just radicals. And so it's a totally different type of mechanism. Do you remember in the mass spec section where I showed you that those curved arrows with only one barb on them, and I said they represent the flow of one electron? That's the kind of mechanism we need to answer the anti-Markovnikov. So don't worry, all will be revealed later on. We'll see the whole thing. But this is what we need to know for now. Let me give you guys a second. And it says here, predict the products for each of the following reactions in the cases where you get a stereocenter. Draw both enantiomers. I'll tell you what, you don't have to draw both enantiomers. Instead of drawing both, I accept if you just draw one and then you just write plus enantiomer. That's good enough for me. If you just draw one of the enantiomers and then you put plus the other enantiomer, I will accept, okay? That's perfectly reasonable. So if you're still struggling with it, or if you are struggling with it at all, let's just try this one here. So I have a carbon highlighted in yellow, another one highlighted in green. Let's try okay, make sure I sorted it out in my brain. Which one is going to accept the proton? Will it be the yellow one or the green one? It would be the green one is going to accept the proton. Exactly. Now, let me ask you guys, when you put this bromine on here, I'll just, and I'm going to erase some stuff here. Is that a chiral center, what I formed there? Is that a chiral center? Yeah, absolutely, right? That carbon has a bromine, a methyl, an ethyl, and a propyl. And so what we should do, and so I'm going to do a little bit of erasing here, get creative, right? Is I should say, well, I'll put the bromine on either a dash or a wedge, doesn't matter. You choose. If you put it on a wedge, that's totally reasonable. And then you can just write plus enantiomer, and I will accept that 100%, okay? In fact, I think in the textbook that's how he does it, okay? I think he just writes plus enantiomer. So could I give you a second to try to draw the products of the other two and see if you get enantiomers? If you don't, that's totally cool too. Just check. Second one with the HCl. Do we get a stereocenter in that one? No, there's no chiral center in that molecule. Somebody drew it with a dash and a wedge. That's fine. As long as you don't write plus enantiomer, I'll know you know what you mean, or what you mean by that. And so, and another thing, lovely, I was walking around and saw a couple of people draw mechanisms. Didn't even ask you to do that, but I saw some people drawing some beautiful mechanisms. Something that is a little bit annoying with the textbook is that if you do want to draw a mechanism, a lot of times you have to redraw one of the starting materials. So what I mean is this. If you wanted to draw a proper mechanism for this, you kind of have to, you do have to redraw the HCl so you can show the bond between the hydrogen and the chlorine breaking, right? But if you want to draw a mechanism, you go for it, okay? So I'll just draw something like this. I'll pencil out the intermediate. So our intermediate is this carbocation. Now, since the intermediate is not isolable, we don't isolate that. Sometimes we put it in square brackets just to mean it's an intermediate, okay? It's nothing, it's not a product or anything like that. So now we're going to take our chlorine, and you've probably seen me do this in class a few times where I'm too lazy to draw the lone pairs around the chloride, and I just draw the curved arrow off the negative charge. I accept that, if you don't feel like putting in the dots right away, but as you guys stated, there's no chiral center in this molecule, and therefore we end up with something that looks like that. What about the last one with the hydrogen iodide? Did we get a stereocenter in here? Yeah, sure we do, okay? And again, you can draw a mechanism if you want to, and if you don't want to, that's totally fine as well. I'm just going to draw, so we're going to have our iodide on here, so we're going to have our iodide like this, okay? and then we can just put plus enantiomer. I remember when I was a student, my instructor taught it this way, where he would do what I do, or I do what he did, or I'll let you guys try it, and then he would write down the answer, and he would put it on the overhead projector. It was very old school, right? He had a marker, you know. And I remember, I'm not an OCD personality, or at least I don't think I am. I've never been diagnosed as such. But I remember being annoyed by this, is that if I put the iodine on a wedge and he had it on a dash, I'd be like, it would annoy me. But again, if yours is the opposite of mine and you wrote plus enantiomer, we have the exact same answer, okay? So it's all good. All right, there you go. Markovnikov's rule. What do you think? Pretty reasonable rule? Well, guess what? We're going to get to apply the rule again. We're going to apply the rule again, okay? So let's take a look at hydrohalogenation in terms of what can happen with those carbocations. Do you guys remember from quiz 6 when I said, or in chapter 6, I said, if a carbocation can rearrange to make a more stable carbocation, it will happen, right? It always happens. And thus, since you guys know the mechanism now, right, you understand how it works, the rich get richer, now I want you to add that to the mix. I want you to say, okay, I know what the carbocation is going to look like. Is it going to rearrange? Therefore, if you need to write out the structure of the carbocation, do it. If you can look at it by inspection and say, you know, that's going to rearrange. Yeah, I got it. Okay, totally fine. Okay, but you have to be able to evaluate that. So if you had, you know, let's say something like this as a starting material, right? And if you added a proton to it, it's going to add to the carbon on the end to give you a secondary carbocation. But you would look at that and say, well, this secondary carbocation is going to undergo a hydride shift to give me this tertiary carbocation. Then my nucleophile is going to come in like that. So when this alkene undergoes hydrohalogenation, the secondary carbocation could rearrange to form the more stable tertiary carbocation. What I really want you to be able to do is to be able to recognize it. And so again, like you guys just said, if a carbocation rearrangement can occur, they do occur. And so usually what I'll ask is, you know, draw both products or draw the more stable product or draw the major product. The major product is going to be the product of the rearrangement. Okay, so we'll just put major product in there. Now, let's see if we can propose a mechanism for this. But if you're, you know, wondering about mechanisms, something that we can do sometimes as a strategy as organic chemistry students is we can say, okay, let's look at the carbon skeleton. I used to do this all the time, or I would just highlight the whole thing with my big yellow highlighter. And then I'd say, okay, I'm going to highlight the carbon skeleton in the product. So then I'd grab my highlighter and I'd highlight, again, only carbons. And then I'd say, did the skeleton change somehow? Can you guys see that the skeleton is changing? Right, you have those two methyl groups on the same carbon, but somehow one of those methyl groups moved, right? Therefore, what happened, right? There was some kind of methyl shift along the way in here. Are you with me on that? This is one of the things I love about organic chemistry. It's just kind of thinking about, okay, I know there's some kind of change in the carbon skeleton. There's obviously a methyl shift in here. But then it brings up another question, which is, if I just redraw the starting material, and just bear with me here, if I highlight this carbon in yellow and this carbon in blue, now both of those have one hydrogen. You're like, well, I can't apply Markovnikov's rule because the rich get richer. They're both equally rich. Okay, I can't use that. That's true. However, there's only one of them that actually accepted the proton. Can anybody tell me which one it was? It's the blue one that's taking it, isn't it? Right? Because the carbocation, in order for it to rearrange, it has to be on the yellow carbon. You with me on that? If you added the proton to the yellow carbon, you'd have a carbocation where the blue highlighter is. That's not going to rearrange, right? So we kind of put that together in our mind, and we put it all together in one big sandwich, and we say, okay, when this reacts with the HCl, okay, and we're going to redraw our HCl molecule. So we'll put our HCl like this, okay? So we're going to get our proton transfer on that carbon there. So that's why I dragged my curved arrow through that carbon. Again, I do it for instructional purposes. And so we end up with this carbocation like this. So what I would like you to do is I'll give you a minute, try to pencil down the rearrangement mechanism, and then the last step to give you the final product. Okay, give you a second to give that the old college try. It's only a couple more steps. All right. Anyhow, so Mr. Dion didn't put in one of the arrows, did he, right? I didn't put in this arrow here, right? So we have our carbocation, and as Luke was saying, we have to draw an irreversible arrow here because the methyl group is shifting to make the more stable carbocation, which we've got here, like this. And so what's our last step going to be? Attacked by who? The chloride ion, right, which was formed in the first step. So the chloride is going to be your nucleophile. So I'll just draw something like that, and there you go. All right. I think this question is very well done, or I think it's very well thought out. And it wasn't my question, it's Dr. Klein's question, but I think it asks a few things. Right? Do you understand carbocation rearrangements? Are you able to figure out and put all of this together? There we go. We got to move forward. And again, that whole idea of Markovnikov, you're like, I need more practice. Like I said, we're going to revisit it in this section here on hydration. Okay, so the first section, if you didn't catch it, again, was hydrohalogenation. Hydrohalogenation, I'll just review, is HCl, HBr, or HI. One of those three molecules being added to Markovnikov's rule. The only time we do anti-Markovnikov, if you're astute, you probably noticed it's only with HBr, and that's true. Anti-Markovnikov can only be done with HBr. The reasons why will be discussed more in Chapter 10. But if we move on to hydration, right? You guys know what hydration means, right? It must involve water. But as I told you last class, the way we're going to think about our water is we're going to think about it more like this. We're going to think about it as having a hydrogen and an OH group. The OH group, the proper term is a hydroxyl. So we've got a proton and we've got a hydroxyl. However, water is not going to be strong enough electrophile to just react with a double bond, and therefore we need aqueous acid. So our water is going to be delivered from a hydronium molecule is where it's going to come from. So we're going to draw a lot of hydronium molecules. Now, where do you get a hydronium molecule from, or a hydronium ion from? You get them from a strong acid in water, right? There's an equilibrium between hydronium and the conjugate base on whatever strong acid it is. And so when I took this class, again, 30 years ago now, my textbook, she barely ever wrote H3O plus over an arrow. She would usually write this. She would say H2O, right, because that's what we're adding, and then she would put a strong acid of her choice, HCl or sulfuric acid, right, and she would put it in square brackets. Now, I know you guys remember the square brackets from general chemistry. We used them for concentration. They're still used for concentration in this class. However, when they're used over a reaction arrow with a reagent put in there, it means a catalyst, okay? So square brackets mean a catalyst. We're going to see square brackets all the time. We're used in this class frequently. Okay, square bracket just means a catalytic amount of sulfuric acid. Thus, if I get into the actual mechanics of what you would do in the lab, it would mean you would have to have 1 mole. If we talk about stoichiometry, you'd have to have 1 mole of this, 1 mole of water, but then the sulfuric acid, you could get away with 0.1 moles, right? Because it's a catalyst. It gets recycled over and over and over. Very environmentally friendly way of doing chemistry. All right, now the same logic is going to apply. When we react the double bond with our hydronium molecule, and you gotta be able to draw hydronium by now, right? If you react it with the hydronium molecule, again, the rich is going to get richer. So if I draw a curved arrow like this, okay, what's the intermediate that I'm going to form? Now I don't have room to draw it underneath, so I'll draw it over here. It's going to be this tertiary carbocation. Carbocation is what we would get. Are you with me on that, right? The secondary carbocation is less stable, higher activation energy, the whole shebang, everything we saw with hydrohalogenation. Great. And so in this section, he takes it one step further and he says, you know what? The rates of reaction, right? Like rate laws again, right? But just looking at the relative rate of reaction for the addition across ethylene, propylene. So this is ethylene, this is propylene, and this is called isobutylene. If you're good at memorizing common names, this is isobutylene. So we got ethylene, propylene, isobutylene. Well, ethylene, after protonation, gives you a primary carbocation. Okay? Propylene would give you a secondary carbocation, and isobutylene would give you a tertiary carbocation. You with me on that? Okay. You can see the relative rates. If we assign a relative rate of 1 for the formation of the primary carbocation, you can see the formation of the tertiary is 10 to the power of 11 times faster. So if we were to assign the 10 to the power of 11 a rate of 1, you can see that the formation of the primary carbocation virtually, is so slow, it's completely useless. All right? And what he's telling you here is he's kind of exposing you a little bit to, the whole rationale behind mechanisms. How nobody's ever recorded a video with their iPhone of electrons moving around. Oh, there's a nucleophilic attack. Oh, look at that, a proton transfer. No, that's never happened. And so if you're wondering, what's the evidence for these mechanisms? How do you know that? Well, again, it's based off of data, okay? And these data are consistent with a carbocation intermediate, right? Tertiary being more stable than secondary, being more stable than primary. All right, there's the mechanism. It's the exact same thing we looked at before, okay? The only thing you'll notice is that there's going to be one extra step in here, right? You've got the proton transfer in the first step, okay? And I expect you to be able to draw this mechanism. You've got the nucleophilic attack, but what's your nucleophile now? Your nucleophile is the conjugate base of hydronium, which is water. When water attacks that carbocation, do you get a neutral molecule? No, you get an oxonium ion. And so what must you do? You must take the oxonium, and then water comes back and deprotonates. Now, watch very carefully. Okay, I'm sure most of you probably got this already, but just in case, watch this. What did I tell you? I said the acid was a what? It was a catalyst, right? So the acid, are you with me? A catalyst, remember, it gets recycled over and over and over, right? You only need a catalytic amount. That means you don't need a stoichiometric amount. You can get away with a fraction of the stoichiometry, right? 0.1% or 1%, something like that. So look, we start out with hydronium, but look what happens in the end. After this water molecule picks up a proton, what does that make? Hydronium. So he didn't include it in here, but you can write it down. You can say, yeah, you get the product plus you reform the hydronium. So you see how the hydronium just gets reused over and over and over, right? That's why it's an acid catalyzed hydration, right? We don't need a stoichiometric amount of the acid. There you go. So again, I expect you to know this mechanism, the mechanism of acid catalyzed hydration. Same old rules. The rich get richer. Why? Because you form the more stable carbocation intermediate. And then the only thing you have to add is, since water is your nucleophile, you're going to have to do a proton transfer at the end, but it makes sense because it regenerates your acid what? Catalyst. There you go. There's logic to all of it. Now, do you guys remember what I told you in chapter 7 was one of my favorite reactions in organic chemistry? I said that beating the heck out of an alcohol, right? Remember it said concentrated sulfuric acid. And in chapter 7, it put here heat, right? He said if you heat something, if you take an alcohol, heat it up in concentrated acid, that it makes the most stable double bond. Who remembers that? Okay? Well, there you go. You see that if you use dilute sulfuric acid, right, it's going to do the addition. However, if you use concentrated sulfuric acid, you're going to end up with the dehydrated product. It's all based on Le Chatelier's principle. And if you're like this, there's certain things, I've been studying chemistry for how long? There's certain things I just can't shake. They just will not leave me alone, okay? Le Chatelier's principle is one of those things, right? You hear about it in every chemistry class you've ever taken. You learn it in Gen Chem 1. We never shut up about it in Gen Chem 2 with your Q's and your K's and comparing which way is the equilibrium going to go, right? And now it's back here. Well, let's think about it. If we have dilute sulfuric acid, right, that means we have a lot of water. If there's a lot of water, it's going to push the reaction forward. If we have the dehydration, we're going to be doing it in concentrated sulfuric acid, which has very little water. So that means there's very little water, right? The water is being removed, so it's going to push it back towards the alkene. So again, it's just a matter of Le Chatelier's principle. There we go. If we're synthesizing the alcohol, we would use sulfuric acid and excess water. But if we're doing the converse, if we're making the alkene, we would use concentrated sulfuric acid, no water, okay, or less water. And I would also add heat in there because it's part of the chapter 7, right? Is that we said heat was put in there. This is something we teach in nursing level organic chemistry. We don't cover mechanisms with them, but we do discuss this with them. We try to explain, Le Chatelier's principle, and we go over the idea of when you would use dilute and when you would use concentrated, and we, try to put it into action, Le Chatelier's principle. This slide is just rehashing something that I brought up maybe 15, 20 minutes ago when I said to you, remember that carbon that I drew an arrow next to and I said, what's the hybridization of this carbocation? And you guys were like, sp2. And I said, what's its molecular geometry? And everybody went, trigonal planar, it's flat. And so this is just him saying, well, if you have a carbocation, yes, it's trigonal planar. You got an empty p orbital in there. Thus, the nucleophile, whether it's water, bromide, chloride, iodide, doesn't matter. It's going to be indiscriminate. It's going to attack from each space. And therefore, this is why we get, if we form a chiral center, we can end up with a mixture of enantiomers. But again, just to repeat myself like an old person, okay? Remember, I told you on a quiz, you can write one stereoisomer and just write plus enantiomer. That is totally fine by me, okay? All right, let's see if we can draw a mechanism for this guy. Now again, and I'm not accusing anybody of anything. I'll point the finger at this guy right here who's standing up in front of the class. I'll say, Mr. Dion, I'll put a mirror. Don't be lazy, okay? Mr. Dion, you can't draw a mechanism. Don't be drawing some kind of crap mechanism like that. That doesn't mean anything, okay? That's nothing. That means Mr. Dion needs to get his pencil out and redraw the hydronium so he can draw a proper mechanism. Cool? Now, if I highlight, I'll do it a couple more times with you. I hope I'm not bugging you, but anyhow, it's my job to go over it a few more times, okay? Which one of those two carbons is going to accept the proton from the hydronium? Will it be the yellow one or the blue one? The blue one, right? Because the blue one has 2 protons on it. The yellow one only has 1 proton on it. Thus, and if you want to do the old thing that I do here, where you drag the curved arrow through that carbon, if that helps you, drawing the intermediate, by all means do so. So I want you to draw the carbocation that results. Okay, I want everybody to give that the old college try. And I'll scribble it down here too. The hydride is going to shift, right? It's going to be this hydrogen here is going to shift over. So, Luke, what kind of arrow do we draw?
We only drew irreversible.
Irreversible, exactly. So we'll draw irreversible arrow like this. Here we go. And I'm sure you guys connected the dots on this already, but you're probably looking at it and going, well, look, you have a secondary carbocation here. Sure, that's great, but your hydroxyl's over here, okay? So how the heck did it end up over there? The only way it could have happened is if there's some kind of rearrangement going on. And so what I'd like you to do is I want you to draw the nucleophilic attack and then the proton transfer. There's 2 more steps, nucleophilic attack and proton transfer to get to the final product. All right, so we have the water coming in as the nucleophile. What's this ion called when the oxygen has a positive charge? An oxonium ion, exactly. And so in the last step, the water is going to pull off the proton off the oxonium, right, Kai? And then we end up with the alcohol and something that he left out, but we'll put it in, is that you reform the acid catalyst at the end, don't you? It's not magic, but it kind of looks like it in a bit of a way. So during the quiz, and I haven't even started grading quiz 7 yet, okay? I haven't even looked at it. It's sitting in my office with a big clip on it, okay? I haven't even started. But I got a few questions during the quiz where people are like, they were drawing mechanisms like a step and then another step. So the way you want to draw a mechanism is like this, at least some way that it's abundantly clear. You're starting with your starting material or the product. Cool? Okay? Now again, if you practice your mechanisms, they're gonna get nice and neat and pretty, and you're gonna have a beautiful mechanism for everybody to look at and see all the individual steps. So make sure you practice drawing your mechanisms, okay? Get a blank piece of paper, a pencil, and do not be afraid to put an arrow in the wrong place. If your arrow's in the wrong place, what do? Erase it, right? Erase it and say that was in the wrong place, right? If you ever come to my office, you'll notice I have a lot of scratch paper kicking around. Why? And also you'll notice my recycling bin is full. Why? I make lots of mistakes, right? Practicing something, oh, do that again, fix that. Okay, there, that looks better. So don't be afraid to make a mistake, okay? That's totally reasonable. Now, think about this. So organic chemists are like any scientist, right? They love to probe different reactions and see like, what can I do and what can I not do and that kind of stuff. And one of the things that's interesting about this whole hydration thing and this halohydration thing, and we're going to focus on hydration for the last few minutes that we have in here. But this whole idea of the hydration, when you get the carbocation rearrangement, the next section deals with a question that somebody asked, okay, and answered it. And they said, is there a way we could do Markovnikov addition of water across the double bond and avoid the rearrangement of a carbocation? Is there a way we can just prevent that from happening so that we don't possibly end up with a mixture, which is probably what's going to happen, to be honest, okay? And so, you guys, who could tell me, I've asked you this before, I think, what are the two elements on the periodic table that are liquids in their pure state? You can see they're highlighted in blue up there. What are they? Mercury and bromine, right? And so, you guys probably know that mercury is toxic, right? So the only time we get mercury out in the lab is if we have to, okay? And what I'm getting at is this, is that once we go through this reaction here, which is oxymercuration, demercuration, thus it obviously involves mercury, okay? You can see it right here, Hg for mercury, okay? It involves mercury. Every once in a while I'll have a student who's like, I'm gonna use this for every Markovnikov addition. You can't. The only time it's acceptable to do this reaction is when you're in a specific case where you want to avoid the carbocation rearrangement. Why? Because it's so toxic, it's bad for the environment, right? If we have a case where we don't have to worry about carbocation rearrangements, what are we going to reach for? A catalytic amount of acid, right? We can put that down the drain, for Pete's sake, right? A little bit of sulfuric acid might help clean out the pipes a little bit, right? So if you're like, what is this whole idea of mercury in organic chemistry class? What happened to the protons and the oxygens and the carbons and nitrogens and the halogens, It's a great question. So let's take a look. It says Markovnikov hydration, so our water and sulfuric acid, which are mixed together to make our somewhat ubiquitous hydronium molecules that we see, or ions, that we see in organic chemistry class. It turns out it has a limited application because, as you saw, we can have carbocation rearrangements, and in all honesty, they usually give you a mixture of products, right? You guys looked at a TLC. It has a mixture on it. Maybe you had to identify different components, right? Mixtures are tough. They're tough. They're tough to separate. They're just tough to deal with. And so if there's a way we can avoid mixtures, we will. Oxymercuration, demercuration is an alternative method of Markovnikov hydration, the addition of a hydrogen and a hydroxyl on our double bond. And the beauty of this reaction, no rearrangements occur. Now, I am not, so you can look deep into my eyes, I am not going to ask you to draw any kind of mechanism for oxymercuration, demercuration. In fact, the second step, the demercuration, it even says in your textbook, it's beyond the scope of our class. It's probably a radical mechanism, all this stuff, okay? But, as I always say in class, the more you know, maybe the easier it is to retain the information. And so just let me show you a brief snippet of how this works, and I want to show you something called a mercurinium ion, okay? So the way it works is this, is you have your mercuric acetate. So mercuric acetate is Hg, so mercury, and then we have two acetate groups on there, right? And this acetate group, so OAC, so the AC part is this part here, right? You guys remember from your biology class, acetyl coenzyme A, right? That's an acetyl on an oxygen. So we call that an acetate, right? And if you're like, isn't that the conjugate base of acetic acid? Yep, it is. Okay, so we've got two acetates on this mercury. So it's forming like a complex, okay? Now what happens is that spontaneously, the mercuric acetate can lose one of the acetyl groups, so we end up with a mercuric cation. Now what do you guys know about cations? Are cations electrophilic? Sure, right? Electrophile, seeking electrons. And so when that mercuric cation gets in the presence of a double bond, there's going to be a reaction occurring. And what happens is you end up with this nucleophilic attack by the pi bond. So I'm talking about this part here. He's comparing it to the hydrohalogenation, but anyhow, I digress. The double bond is going to attack that mercury cation, but you notice that there's a lone pair of electrons on the mercury. And what happens is that lone pair of electrons can results in the formation of what we call the mercurinium ion, okay? And you see that the mercurinium ion has two resonance forms, okay? Two resonance forms like that. Are you with me? Okay? So which one of these, or which carbocation is more stable? It's going to be the tertiary carbocation, thus having the positive charge here versus having the positive charge over there, right? But instead of a rearrangement occurring, the mercurinium ion does not rearrange because it has these two resonance contributors, right? Where you have this three-membered ring, you have this three-membered ring here. And if you want to write this down, we'll just put does, or you could put cannot, but does not undergo rearrangements. And so our water is going to attack that stable carbocation, the tertiary. So water is going to come in. Here he just drew it as a nucleophile because I'll show you in a second. I'll probably show you after the break since we have 1 minute left. But anyhow, you can see here the nucleophile comes in, attacks the more hindered carbon, Markovnikov addition, the rich get richer, right? And then the last step is just to treat it with this reagent here, which is called sodium borohydride, okay? Let me just put an amen to it there.